Hi, everyone. Thank you so much for joining. We're going to go ahead and get started. My name is Bree Friedman. I'm a researcher at the National Laboratory of the Rockies, or NLR. This project has been done in partnership between NLR and the Hawai'i Marine Energy Center, or HMEC. And a lot of people beyond myself have been working on this project. So big shout out to all of them. Today I'm going to be presenting on the lessons learned from the Small Underwater Research FLAP Wave Energy Converter, or SURF-WEC. We took this project, the SURF-WEC, we started from design, build, test, and it's currently in the ocean. And so this presentation is really focused on the lessons we've learned along the way, and the overall story of the SURF-WEC. This presentation will be recorded, so you're welcome to access it after. I expect to have about 20 minutes at the end for questions, so feel free to throw questions in the chat or in the Q&A, but also we'll allow you all to unmute at the end so we can have a discussion. And then finally, I'll be talking about quite a few lessons learned, but not all of the lessons learned we've compiled for this project. The end of this slide deck has 5 hidden slides of just those lessons learned listed. I won't go through them in this presentation, but you'll have access to them at the end. So let's dive right in. The SURF-WEC's been going on for about 3 years. I mentioned we have the device currently deployed in the ocean. That's our one ocean deployment. And I mentioned those over 70 lessons learned, which are listed in hidden slides at the end of this presentation, which will be shared. And throughout this presentation, I'll hit on about 30 of those lessons learned. You can see in the bottom a little icon. There's a head with a green box. And that's where the lessons learned will be called out throughout this presentation. Some of them will have LL for lessons learned, and some of them will have PR for practices worth repeating. Lessons learned are things that we wish we did, things we would do in the future. Practices worth repeating are things that we did do, and we think they were a big reason for our success. And then a little bit of context will be shared with the SURF-WEC experience. I do want to note that these lessons learned are not meant to be a standard. They're not meant to be a recipe. They're just meant to be tools and things to think about in deploying a wave energy converter. So the Small Underwater Research FLAP Wave Energy Converter, or SURF-WEC, is the combination of the Hawai'i Marine Energy Center's 1 meter by 1 meter oscillating surge wave energy converter, or a FLAP, and that's what I'll call it throughout this presentation. So HMEC had this FLAP. They had done some testing with it without a PTO and minimal deployment. They did a couple-hour ocean deployment with it. And then NLR designed, built, and tested a power takeoff, or a PTO. And so our one line of our power takeoff is shown here. This is a hydraulic system. I'll get a little bit more into it. And so by combining this power takeoff and the flap, we have the SURF-WEC. And the idea was to combine those two, do a lot of testing, and then deploy for up to 1 year. And the whole idea here, if you look at the right side of my screen, some of you might recognize the HERO-WEC and the Pioneer Array, which are 2 other wave energy converters. And so the SURF-WEC is in there, in that funnel too, of just collecting open source data and lessons learned for the wider marine energy community. And so this presentation's sharing some of those lessons learned that we've collected so far. So you might be asking why we're deploying a small scale WEC. I mentioned the flap is only 1 meter by 1 meter, 3 feet by 3 feet. This is really small when we think about wave energy. So if you think of technology on a staircase, as you walk up the stairs, your risk, your cost, your time are all increasing. On the bottom of the stairs for a WEC, we have modeling. There's a lot of modeling done on different archetypes of wave energy converters. The flap, or the OSWEC type, generally performs really well in theoretical modeling. As you climb further up the stairs, you have a kilowatt scale deployment. And a flap type device was deployed. It was a 12 meter by 18 meter, hundreds of kilowatt scale, deployed by Aquamarine. This is the Oyster device. And the deployment didn't last very long. And this is a common story we hear throughout industry of like, we need to deploy something large enough that is relevant to producing power. Industry needs to do that so that it's economically feasible. But we don't always have the lessons that we need to know to be able to deploy at that scale. And so instead of jumping a bunch of stairs, what we want to do is just take a baby step up these stairs and do a watt level deployment. So the device, the SURF-WEC currently is at an average power of like 1.5 watts. It's very, very small power. We aren't thinking about commercialization in any sense of the word, but we really just want to learn lessons that are applicable to those larger scale deployments, to those deployments that are higher up the staircase. So we're looking at less than 100 feet from the pier. We're looking at a water depth that's about 3 to 5 feet deep. And all of our components, when we bundled them for deployment, the bundles were each less than 1,000 pounds. And this made deployment a lot simpler and a lot lower cost. And so we can learn lessons at a lower cost, lower time, and lower risk because we're not as high up on that staircase. So this project was guided by 3 goals. The first one is deployment. That kind of goes back to that staircase. Learn what is required for deployment, operation and maintenance, and retrieval of a small-scale SLAP device. The second one was looking at a PTO, and I'll dive a little bit more into the PTO that we're using, our power takeoff, but just providing more data for the wider community for tuning simulations, for designing PTOs, that sort of thing. And then finally, and most importantly, is reporting. Just sharing all of our work is open source. Sharing that data, sharing the lessons learned, so that we as a community can walk up the staircase together. And this is our first lesson learned. This is a practice worth repeating of knowing your goals. Having these 3 very clear goals reduced scope creep on our end. And when we're at critical crossroads, we use these 3 goals to help us answer questions. So this is a single image of the SURF-WEC device. So starting out here, we have the spotter buoy. So this is our wave characterization. It sits about 20 feet in front of our flap, which is sitting on a frame that's anchored to the ocean surface. Connected to the flap, we also have a offshore PTO, so our offshore power takeoff. And then we have some cabling running onshore to our onshore PTO, and then also our data acquisition system, which we're using MODAC 2.0. This system is deployed off the coast of Oahu, Hawaii, on the southeastern side. Beyond what is pictured here, we're also looking at permitting, safety, risk, deployment, operation and maintenance and retrieval, and then data dissemination. So getting into permitting, we had to go through quite a long process. It took about 2 years to acquire all of our permits, and this is a pretty simple device. So we learned throughout the process that making permits as broad and all-inclusive as possible is critical. We lengthened our dates. We doubled our time of how long we thought we would deploy. This reduces how often we have to, this reduces needing to modify our permits. We also had a list of optional equipment, which we've ended up using some of that optional equipment. Permits will take longer than you think. It took about 2 years, and this is a small scale project. And then one of our lessons learned here is determining which permits are required as soon as possible before you start pursuing all permits. One of our permits, the Hawaii Department of Land and Natural Resources, the right of entry state permit, took a lot longer than we thought, and we started pursuing it later on because we thought it would be a simple permit. So this actually delayed our spotter buoy deployment. Speaking of spotter buoys, I mentioned that we deployed, that we have that spotter buoy sitting about 20 feet in front of the WEC. You can see it here. We do have 3 spotter buoys deployed. This is the main spotter buoy that we're using for wave characterization. In the bottom right image, you can actually see what that deployment looks like. This is that actual spotter buoy that's sitting in front of the WEC. You'll notice that we're sitting behind a breakwater in that middle image. And so we're at a very protected site. So if you look at the bottom left, this is our wave resource distribution from that spotter buoy that sits 20 feet in front of our device. And so you can see that over 800 hours of our device being deployed, we've been sitting in the 0.2 to 0.3 meters significant wave height and 3.5 second period. And we're generally sitting somewhere around there. You can see the 9 boxes around it, or the 8 boxes around it are similar. And so we're looking at really low wave resource. And again, that's just so we're taking a baby step on those stairs. So I mentioned the PTO. We're using a hydraulic PTO. The reason we chose a hydraulic PTO is for the off-the-shelf components, the scalability. It was easier to marinize and minimal effect from line length. That's thinking about if we scale up, our device will sit further from shore. So we wanted minimal effect from increasing the line length. So the image in the middle of the screen is a one line of how our PTO works. And so we have the flap. So you can see the flap is black. It's in this picture being moved by people when we're doing out of water testing. So we have the flap. As it moves, it's connected to a hydraulic cylinder. So the hydraulic cylinder is extending and retracting, and the hydraulic cylinder has a rod side, which is circled in blue, and a cap side circled in orange. And so it's pumping oil by the cylinder moving. And then we go through a valving system, and I'll explain the valving system on the next slide. But basically, we're pressurizing oil. We're pushing this oil from the hydraulic cylinder into an accumulator. And then once the accumulator reaches 190 psi, so we're working at really low pressures, an on-off valve opens, allowing that pressurized oil to then turn a hydraulic motor, which is connected to an electric generator. Once the accumulator drops from 190 psi back to 150 psi, the on-off valve closes and we start pressurizing the accumulator. And so we're pulsing that wave. We're taking the pulsing wave motion into a higher frequency electric generation. And then once the oil goes through the hydraulic motor, it'll then go back into a reservoir and the process can start all over again. So I mentioned that valving system. So there are 2 different valving systems sitting inside that box. The first one is a passive valving system. This is like a rectifying circuit. So it has 4 check valves, and no matter the direction the flap is moving, energy or flow is always being pulled from the reservoir and pushed into the accumulator. And so you can see the 2 different directions the flap moves. The flow is always in the same direction. Contrary to that, we have the active valving system where energy can actually be put into the flap. So the idea here is you can pull from that high pressure accumulator and push the flap instead of just having the flap push the cylinder. And this theoretically allows the system to be closer to resonance. So short-term loss for long-term gain. And the way this is done is using 2 solenoid valves. And so the connection between the hydraulic cylinder and the accumulator and the reservoir are independent of flow direction. And so a couple of notes here, a couple of lessons learned. Theoretical ideas and practical systems don't always align. We had this design and we took a lot of time bench testing it to get it to work. So increasing time and budget for unexpected experiences is critical. And then also clearly defining what you're using your model for. Thinking about how accurate you require your model to be, but also how scalable you require your model to be. Thinking about, do I want to be able to easily change this accumulator volume if I scale up, for example? So knowing that going in can make your model more useful to you later on. Once we had our design, we got into testing. So we started with component and subcomponent testing, and this was critical for our success. Even though it's adding more time in the front end, it saves time overall. Understanding each individual component and any subcomponents actually changed our full system design a little bit. And so this made our overall testing much shorter. Once we had that component and subcomponent testing done, we went into the full system test. You'll notice that this black piece in the bottom right corner is an electric linear actuator. This is what we used instead of our flap for lab testing that was out of water for characterizing our system and making sure our system worked. On the table here is that valving system. So that has both the active valving and the passive valving, along with the valve selection. So we did a lot of full system testing, and then we marinized the equipment. So this valving system was all put into this enclosure here because it sits underwater, but all of our electronics were also marinized. Even the components that sit on the shore were also prepped for pier weather. And once we marinized, we went back to full system testing again. And then we shipped the system. And again, we tested the full system. This is when we integrated the flap with the PTO. This was the first time connecting the HMEC equipment with the NLR equipment. So we were testing that before deploying in the ocean. A couple of notes here. You'll notice that we tested the full system 3 different times. Test it as much as you can. Each of these times we learned new things. Each of these times we had to slightly change things. We had to fix things. If it doesn't work in the lab, it's not going to work at sea, and it's much easier to fix in the lab. And then prioritize function over performance. I think in marine energy, a lot of times we get lost in performance characterization without the focus on does it work and is it going to work for a week? Is it going to work for 2 weeks? Is it going to work for a month? So just really prioritizing function. I want to take a note and dive into this this full system testing after marinization where we learned some lessons. So after marinizing, we had some expectations. We expected the system will perform as it did pre-marinization. We were just, we unplugged things and plugged them back in a box. It should be a simple test. We expected little time required. In reality, the system initially didn't work. The first issue we found was that there was a bunch of air in that valving system that we had introduced during marinization, and we were really struggling to get it out. And so we tracked air bubbles. And a lesson learned here was designed for easy flushing and purging of hydraulics. What we ended up doing was adding these bleeder ports throughout the system because a lot of our hydraulics were horizontal runs. And so it was quite difficult to get air out of the system, and air is no good in a hydraulic system. So designed for that initially. As we were tracking this air bubble issue, we didn't really look at the rest of the system. We saw the issue and we dove into it. And this was another lesson learned. We should have taken a note here of, okay, we need to fix the air bubble issue, but let's also dive into, is everything else working? We found that our generator and our torque sensor had both stopped working. And so it pushed back our timeline having to fix these independently rather than fixing them at the same time, or starting to look into them at the same time. So evaluate the whole system before focusing on individual issues when you can. This took multiple weeks of troubleshooting, and one of the reasons we were doing this testing is because we wanted to test our procedures before deployment. And so this was critical. We had oil flushing, air purging procedures written out, and these got entirely changed based off of what we learned during this testing before we shipped the equipment. This actually made us switch to shipping the equipment filled with oil, and so our dry commissioning was a lot smoother. Moving on to dry commissioning, and I'm sorry this photo is not showing for some reason. Moving on to dry commissioning, this is the first time we integrated the flap with the PTO. The system, we tested the system after shipping before deployment, and expectations here and reality really matched. Let me see if I can get this figure to show. right, there we go. So here we did a really good job emphasizing how these different components would fit together. Even though the flap and the PTO had never been in the same room until dry commissioning, the two teams worked together and talked through every connection point, making sure that all of our measurements were the same and that we were on the same page. We also scripted out very detailed procedures, so everyone was on the same page prior to deployment. And in that same vein, in-water personnel was a part of setting up the system prior to deployment. A lot of times your divers are going to be different personnel than the people who have been testing the equipment or designing the equipment. Everything is harder in the ocean, everything is harder underwater. And so having them set up the equipment, know how it's set up, know how it needs to be unraveled for the hosing, and doing that in the lab was critical to making it smooth in the ocean. Once we finished dry commissioning, we thought we were ready for deployment, but we had a weather event come up. In the planning, we were told by local team members that let's have a 3-day weather contingency. We will never need it though. If you think of Hawaii weather, you expect a clear, calm day. In reality, Oahu experienced a historic storm, and the entire weather window was required. The pier was actually shut down for high winds, so we weren't allowed in the pier. And so we're really thankful we had that weather window. So even if you expect to never use it, include a weather contingency. It's always better to finish early and not use a contingency than not have a contingency at all. Trusting the weather judgment of local team members, as we saw the storm coming, they were able to advise us on the severity of the storm, what that would look like in the ocean. They know the location best. And then prepare your equipment. Once you are deployed, prepare your equipment for the worst weather immediately. Don't say you're going to do it next week. A weather storm might be wrong, or a weather forecast might be wrong. Once we got through the Kona low storm, we did deploy. We deployed in sections with a forklift, which you can see in the bottom right is our valving system and our hoses being deployed. For deployment, we had 2 divers and 2 to 3 swimmers. And system was stable immediately after deployment, which is a huge, huge win. Here, expectations and reality really, really matched. And we think that we had one clear deployment lead, and we held daily plan of the day meetings, and both of these really led to our success. These ensured that the entire team was on the same page, and any major decisions, one person knew about them all, and so we weren't making contradictory decisions. When you are designing a system, don't just think about the longevity in the ocean, don't just think about power performance, but also think about those deployment activities. Those a lot of times can be the highest load or highest impact activities on your device. And so design for those and however long you want your device to last in the ocean. During deployment, our most complex piece to deploy was probably the flap itself. We expected that our flap has a port for purging it of water, but also filling it with water so we could make it less buoyant. Our flap has about over 500 pounds of buoyancy, so hard to sink into the ocean. So our team had done testing to fill the flap with water so it would become more neutrally buoyant, and they expected it to take about 6 minutes. And we expected that the flap would be easy to maneuver once fully flooded. In reality, time in the water feels different than in the lab. We did not time how long the flap had been was filling with water before the team was like, all right, that's long enough. Let's get to deploying. When you're standing in the water or swimming in the water, time feels longer. You don't want to just be floating around. So the flap was slightly buoyant through all of deployment. And this caused a difficulty in aligning the flap with the flap anchor. So some of the thoughts here was choose your tide intentionally, because the flap was buoyant throughout all of deployment. If we were deploying during low tide, the flap would have been sticking out. The top of the flap is surface piercing, so we would have needed less water in the flap for it to be buoyant. We deployed the flap anchor, which you can see in the top right image. There's a frame which is anchored down, and this is what the flap connects to and rotates on. We deployed this before deploying the flap, and that was critical to aligning our getting the flap in the location that we wanted. So the frame was a lot easier to handle than the flap is in the water. And then finally, in terms of the difficulty aligning the flap with the flap frame, we are considering using guides if we were to do this again to make it easier to mount the flap to the anchor. After we deployed, we looked at the system 24 hours into deployment. The system was fully operational, but we did find a fitting to be rusty. And so you can see that in the bottom left image with the yellow arrow. You see a rusty fitting. In the top image is that same exact fitting. You can see the orange tape. It's the same exact part. And so we pulled the part number from it, and it was the same part number. This was a part that was sold as 3/16 stainless steel. We deployed 5 other of these exact fittings. They're deployed underwater. You can see one in the back right of the bottom image. The part number looks correct. We bought it from a reputable supplier. So we, 3/16 stainless steel is not gonna look like this 24 hours into deployment. So something we've learned here or are considering in future is testing components with a magnet or testing them in salt water. This hadn't really been thought about before. We don't expect this to be a common issue, but it's something to think about. Post-deployment, we have some remote monitoring. So I mentioned we're using MODAC 2.0 for our monitoring. And so you can see the left image is what I can see from my desk in Colorado to check it on the system. And I can also look at this live video feed. And so this is from the same minute of data on May 21st. During this time, our spotter buoy was reading about 0.42 meters significant wave height for a second period, and our device is getting an average power of 6.4 watts. So this is a much more energetic condition than we generally see. This is also, I should note, the MODAC data is just a minute of data. The spotter buoy data is 30-minute average. So I'm sure there's some misalignment there. But 24 or a day into deployment, the pier lost power, and our MODAC system is powered from pier power. And our MODAC system thankfully automatically restarts after a failure. And so even though we didn't collect data while the power was out, the MODAC system automatically restarted. And so we were alerted with a text message during that restart, so we knew that the system had restarted, and we could check up on it from Colorado to make sure it was operating properly. The current status of the system continues to operate properly, producing power and collecting data. We're 146 days in. We've collected over 3.3 terabytes of data. We've produced almost 6 kilowatt hours, and our average power is sitting at about 1.7 watts. This video is taken about a month into deployment, so you can really see how much biofouling, how much growth is on the system about a month in. So here we have a first in line sensor. This is our position sensor. You can see it sitting next to the hydraulic cylinder. So this right here is the position sensor. This has been super helpful for understanding if there's an issue with our system or yeah, if there's an issue with our system. So we know how much the flap is moving or how much the hydraulic cylinder is moving from this position sensor. And so we can use that to see if we're getting the power we expect from the bench testing data. And so even no matter what the wave condition is, we can then just look at our first in line sensor and have a really good understanding of if we have a leak or if there's an issue with our system. And then testing fail-safe conditions. I mentioned this with MODAC 2.0, where that MODAC 2.0 does restart, but we do have an issue with our programmable DC load, where all of our electricity is just being dissipated through a programmable DC load, and this does not automatically restart. And so whenever we lose power, lose pure power, somebody has to go to the pure and restart that system before we're actually creating electricity. We're still collecting data before they do that, though. Final note on the current status. This is our power matrix that we're slowly building. So you can see this is similar to the wave characterization matrix that I showed earlier. We're generally sitting in that 0.2 to 0.3 meter, 3.5 second significant wave height, and we're sitting around 1.8 watts as we're for average power, with occasional higher energy conditions. So I want to return to that staircase and talk about the impact of this project. As we all know, theoretical knowledge does not equal practical knowledge, and so it's important to take baby steps up this technology staircase so that we can learn beyond modeling before we put too much risk, too much cost, too much time, and a lot of risk into a project. So small deployments are generating useful lessons learned for data, and data for larger systems. And here, the larger, the more you update your documents regularly, the larger your impact is going to be, and the more that can be learned from the project. A short note on future work. I mentioned that this is going to be deployed for up to a year, so we're continuing to monitor the system. We're working on testing tunable parameters. Obviously, we have some occasional maintenance and we will retrieve the system. We're working through some data processing. We've pulled about 4 terabytes of data that we're processing right now. We're starting to analyze and we'll upload to MHKDR along with lessons learned, and then continuing to update these lessons learned. This project is in no way over, and so nor is the lessons learned document done. And with that, thank you all so much. I would love to open the floor up for questions. I also included my email here. If you have any questions, feel free to reach out there too. Feel free to put questions in the Q&A or the chat or unmute. Did we have a backup first in line sensor in case biofouling broke the first one? Great question. We did not. So that position sensor was our first in line sensor. We do have pressure sensors on the either end of the hydraulic cylinder. So they're not too far from the position sensor itself. But no, we were unable to have a backup. Yeah, what plans or goals do we have for the large amounts of data being collected? So right now we're working on processing it to clean it up, do some quality control to make sure all the data is is good data, and then we're gonna be posting it on MHKDR. And really, the idea here is to make it accessible for the larger community so that it can be used. I think there's a ton that can be done with this data, just diving into the PTO data, but you can also evaluate the wave characterization versus the hydrodynamic models of the flap itself. So there's a lot that can be done there. It's still open to what will be done, and I think our biggest goal is just getting it out to the wider community. Is there any parameter we wish we were monitoring from either the WEC or the area around the WEC that we're not currently monitoring? Great question. I think my answer would probably be water depth, so like tide. Because we're in such shallow water and our device is so small, the tide does make a huge difference from like I think during lowest tide we could have like half the flap sticking out of the water versus the flap fully submerged. And so I think having a pressure sensor, like some sort of water depth meter at the device that was integrated to MODAC 2.0 would be really nice. We do have some tide data that we're able to use, but it's like NOAA data that we then have to, sync with our data that we have. Would permitting have been simplified by putting the system on a small barge? I don't think so. I think as this is a DOE funded project, so for any DOE projects, any government funded projects, you need to go through the NEPA process. And so that does make permitting a little bit more complex to make sure that we're not having a negative environmental impact. What priorities did you take into account for which data was collected? Was there any local consultation done to see if there was some data set that could have an overlapping use for local goals? We were very focused on collecting data for the PTO to understand. Most of our measurements are around the PTO itself. So that's very specific to our device and very specific to the wave characteristics that are coming, that are showing up at the site. And we are also looking at wave characterization of the surrounding site. Our partners HMEC were interested in relating buoys that are permanently set around Oahu to our spotter buoys to see if they could find relationships there. I don't know if that fully answers your question. Feel free to unmute or write another question if it doesn't. Is there any plan to upload the bill of materials of this deployment? It would be great if you could comment on the mooring system of the flap. All right, the bill of materials, yes, we have a pretty accurate bill of materials that we'll upload with the MHKDR submission or MHKit submissions. And then the mooring system, so I mentioned you can kind of see the frame sitting here. So the flap, both the valving system and the flap sit on different frames. These frames were, especially the flap frame, you can see that it's pretty long to reduce the amount of anchoring that we needed because of the moment that the flap's applying to the hinge joint. So we have chains, we have a few 100 pounds of chain sitting on each corner, and then also stakes driven in because this is on a rocky bottom. So we were able to drive stakes in. Did biofouling reach an extent that it became a problem? And would you use any anti-biofouling coats if you did this again? So the flap is painted in an anti-fouling coating. And so if I go back to that video, you'll see that the flap itself really doesn't have much coating on it, or much biofouling, sorry, on it. The biofouling we've seen so far has not been an issue. You can see here that the hydraulic cylinder and the position sensor, because they're moving, they're kind of keeping the portions that they're moving pretty clean. So we haven't had an issue there. The spotter buoys we have had, and I think this is common with spotter buoys where you just maintain them and wipe them down occasionally, so to keep their wave characterization a little bit more accurate. But we used anti-fouling paint on the flap, and otherwise for the PTO itself, we haven't really been concerned about it. These are all great questions. Did we see any wildlife interaction with the flap? I have seen a couple of videos of like fish swimming around the flap. There is PNNL, the Pacific Northwest National Lab, actually set up this video feed. And so we have some live feed and they're monitoring, they're doing some environmental monitoring. They have hydrophones in the water around to look for sound, or at least they deployed that for a day. I'm not sure if that's deployed long term. And then they have some video where especially at night, because of the spectrum of the camera they're using, they're able to see wildlife interaction. So they've been looking into that a lot more. Thanks, Andrea. Yeah, at least one monk seal, is sea turtles, and fish. So would real-time current measurements be helpful? I think the team that's been checking the system and diving. I'm not a diver. Have been checking, have been feeling current, and so having a current measurement would be helpful. Just more learnings there. So yeah, thanks, Joe. Yeah, the hydrophones were just for the day. Any other questions, comments, thoughts? Feel free to come off mute.
Had a wonderful presentation so far. This is Deveni, by the way. Oh, someone else asked a question. I was just going to be curious if you measured anything that at the end of this project you guys are realizing, we really didn't need that sensor there.
That's a great question. Yeah, something we actually learned pretty early on was that a lot of our flow measurements aren't super helpful. We learned this in component testing, where most of our flow meter measurements throughout our hydraulic PTO just are too slow of measurements for the frequency of our device. And so if I were to rebuild it, I wouldn't include those flow measurements. The reason we did still include them in the system was just because they also had a port for the pressure sensor. So we needed them anyway. They didn't really have pressure drop, so we weren't concerned about the losses from that. And we are using one of our flow meters off of the out of the hydraulic motor. That flow meter has been useful. But yeah, that's a great question. Are there plans to scale this WEC to a larger system for continued research? Not at this time. Yeah, we'll see how the rest of this goes and then move from there. But the data will be shareable so that if we don't do it, others can. Yeah, thank you all. Again, feel free to unmute or put any last questions in the chat. If not, thank you so much for joining and feel free to jump off. That's a great question about the storm. So the deployment was delayed because it was unsafe conditions on the pier. The wind was just so high. The wave conditions actually weren't that extreme. So we did, because we're in a pretty protected site behind that breakwater, our risk is a lot lower of extreme wave conditions, and we did over design as you should any wave device for those low frequency storms or those storms you don't expect to happen. But if our device had already been deployed, it would have been fine during that storm. It was really just that we couldn't be working on the pier during that time. All right, if there are no other questions, I think we're good to call it. Thank you all again.